So hello and welcome everybody. My name is Kevin Grenier. This is going to be a web seminar on multi-reference transfer path analysis. And I'm going to go through some slides and I'm going to spend some time in the software and walk you through all the steps that you would use in order to do a multi-reference TPA. Here's a slide showing the differences between a single reference transfer path analysis and a multi-reference. And most questions I get in most TPA studies are single reference problems. And that means there's a fixed phase relationship between fully coherent points. One reference point to reference all the phases to, and an example is engine noise. So if you think about it, if you can calculate orders, and there is a consistent phase relationship between all of the orders throughout the vehicle, whether it be a car or a truck or a lawnmower or an airplane, and if there's a consistent phase relationship between all of those orders across all of the data points, or if you're calculating stationary averaged spectra, and if there's a phase relationship between all the different data points, that is a single reference problem. So in the example shown here, if I have an engine driving a powertrain, driving a drive shaft, driving a rear axle, maybe driving a front transfer case, and I have steering pumps and all these different accessory drives all hooked up to that, there's a phase relationship between all of those different orders, so that would be a single reference problem. A multi-reference problem, which we're going to talk about today, occurs when there's not a fixed phase relationship between partially coherent measurement points. And the example we're going to use here is road noise. So if I'm driving down the road, and if I look at the left side of the vehicle and the right side of the vehicle and the front wheels and the rear wheels, there's not a fixed phase relationship between those measurement points. And part of that is because I'm going over the same portion of road through a phase delay. So there's going to be a difference in phase as I look at all those different response points. So there's not a fixed phase relationship. And we have an issue if we were try to treat that as a single reference TPA problem. I also get questions sometimes on different frequencies. So if you've got multiple components and they're operating at different speeds or different frequencies, we can treat those also as single reference TPA problems because most of the TPA solutions solve on a frequency line by frequency line basis. So if your sources operate at different frequencies, we can treat those as single references as well because we're not combining them at the same frequency. So a typical example is a road noise transfer path analysis. When systems are excited by multiple partially correlated sources, road-induced noise in the car is one example. Engine and air conditioning noise could be another example. Why do we need to treat it as a multi-reference TPA? And that's because there's not a fixed phase relationship between the different response degree of freedoms. Interior sound field consists of multiple incoherent phenomena. Operational data needs to be decomposed into independent phenomena. So we're going to take your operational data that has these partially correlated phenomena acting on it, and we're going to separate it into its principal components. So we're going to do a principal component analysis on your operational data and then feed that into transfer path analysis. Multiple reference signals are needed, so you need more than one reference channel. Analysis for each independent phenomena separately. And then results for independent phenomena can be superimposed in an RMS manner. So basically, we're going to calculate transfer path analysis results for every individual principal component acting on the system. And then since there's not a phase relationship between those independent phenomena, we're going to sum them together in an RMS manner to get the total contribution along each of your paths. And hopefully that's made clear as I go through the slides and as I go through the examples. So here's an example of engine noise transfer path versus road noise transfer path. In a traditional or more common engine noise TPA, engine noise is generated by multiple coherent forces acting on the mounts. There's a fixed phase relationship between the different responses. You've got one coherent noise source. A tacho train or some type of a pulse can be used for engine acceleration as a phase reference. So I can have a reference on my tacho, or I can do an accelerometer on my engine and use that as my phase reference. We can calculate phased reference waterfalls, and from that calculate phased reference orders, and we can use that in a single reference transfer path analysis study. For road noise is generated by multiple partially incoherent forces acting on the suspensions. There's not a fixed phase relationship between the different responses. We have multiple incoherent noise sources. We're going to take that operational data and decompose the operating data into its independent phenomena, and those are the principal components. So each principal component is an independent phenomena acting on the structure at each frequency. Multiple references are needed, so you need more than one reference channel. Transfer path analysis will be done on each independent phenomena separately. We're going to add up the contributions of the different principal components in an RMS manner, so they're going to be superimposed energetically. And we're going to use a multi-reference TPA to do that study. So here's an example of a vehicle, and we've got a couple of targets inside the vehicle. Those could be microphone targets at the driver and passenger ears, or they could be structural targets like the steering wheel or the gear shifter or the outside mirror, something like that. We're going to have indicators, and we're going to have references. And if we're going to consider that we have R incoherent sources and we have M responses, those are your target responses as well as the indicator responses that are going to be used to calculate the forces. And then you've got your references, which are either going to be the wheel center vibrations or possibly the microphones in the car. The number of references need to be larger than the number of sources. So that's why on the slide back here, I said that multiple reference signals are needed. So if I think that I have 2 or 3 independent phenomena acting on my structure, that means I have 2 or 3 sources acting. I need to have more than that as references. So I'm going to need to have at least 3 or 4 references. If I think I have inputs from the road and I have maybe 6 or 7 independent phenomena acting on the structure, then you need to have at least 6 or 7 references. So the number of references will depend on how many principal components or independent phenomena you think you have. So here's an example of the road noise again. Frequency content is coming from the road input, and you've got these independent sources. So here we've got them for 2 wheels called S1 and S2, and it's difficult to separate S1 and S2 to get their independent phenomena acting on it. So those S1 and S2 are partially correlated. And if I look at the front versus the rear, the same frequency content, but there's not a fixed phase relationship between the front and the rear. So if we look at the target and indicator data, so this would be the targets we're investigating, and the indicators are usually accelerometer or strain gauge measurements that are going to be used to calculate the force. Both those targets and indicators have multiple incoherent phenomena acting on them. So what we're going to do is we're going to take that data, decompose it into the principal components, and use that as part of the study. And then the last slide there shows that we're going to combine them in an RMS manner. Okay, so now we're going to talk about how we go about that through singular value decomposition. So we're going to take the operational data, or we're going to measure it on the road, and we're going to calculate multi-reference cross-power spectrums. So if you're doing that in spectral testing, spectrum testing allows you to turn on multiple references. So you could get your operational data for cross powers in spectral testing by turning on multiple references. Signature acquisition doesn't let you do that. Signature acquisition only lets you turn on one reference channel. So we're going to need to process that data in throughput processing with an add-in called multi-reference processing to allow you to calculate those multiple reference cross powers. And I'll show you how we do that in the software. And then if we look at that cross power, the cross power at position X that's non-coherent with reference Y disappears when averaging. So if I have a response at X that is related to an input at Y, as I do averaging, the part that's related to the input at Y stays in the cross power, but the part that's not consistent with Y would average to 0. That's the way the cross power calculations work. So GYX1 is a cross power at response Y due to X1, and that only contains the coherent part of Y that's coherent to reference X1. If I look at the cross power at Y due to the reference at point 2, GYX2 contains the coherent part of Y only with the reference at position 2. So the response is influenced by the two sources, S1 and S2. So that's how we calculate the cross powers. If our sources, S1 and S2, were perfectly uncorrelated, if we were to look at the lower left matrix, that is the reference auto-power matrix. And when we look at the reference auto-power matrix, we only have values on the diagonal. So technically, the auto-power at 1, the auto-power at 2, and the auto-power at 3, 3 have values, but all of the other ones would be 0. So if I have a cross power that is at 1 with respect to reference 2, or the cross power at 1 with respect to reference 3, those ones would be 0 because of the off-diagonal terms. And if you use the modal testing, if I put multiple shakers on my system, if you ensure that the shaker inputs are going to be perfectly uncorrelated, this is what it looks like. The auto power matrix, or the reference auto power matrix, will have values on the diagonal, but the off diagonal terms will always be 0. That's why we can do a multi-reference modal test, because we have to ensure that those references are perfectly uncorrelated. And if you use any of the test lab tools to send out those output signals to drive the shakers, we ensure that those forces are going, or those references are going to be uncorrelated. If you have partially correlated references, you see the reference auto power matrix on the right side. Now we have values on the off diagonal terms, and those cause issues when we do transfer path analysis. And that's only true if the references are partially correlated. You would see them at the right side of the matrix. If the references are completely uncorrelated, you would see the matrix on the left side with values on the diagonal set to 0. So what we're going to do is we're going to take our cross powers. We're going to do singular value decomposition on the cross powers. And we're going to break that analysis up into multiple uncorrelated single reference problems. And what we're going to do is we're going to do that through singular value decomposition. And once we do that, they're perfectly uncorrelated, but we have no phase relationship between the different references themselves, but we have a well-defined phase relationship for all responses with respect to one reference. So basically, within each of the principal components we find, there's a phase relationship within that principal component for all responses, but there's not a phase relationship between principal component 1, principal component 2, principal component 3. There's only a phase relationship within the principal components, not across different principal components. Okay, so in practice, at least for road noise, the references are always partially correlated. So we see this reference auto power matrix on the left side, which has values on the off diagonal. And then when we calculate the cross powers, which is the response multiplied by the complex conjugate of the reference channel, we see the matrix on the right side. So the objective in principal component analysis is to find a transformation enabling the decomposition. So we can modify the cross power matrix with some type of a transformation such that the reference auto power matrix, which is the bottom left matrix, only has values on the diagonal using these virtual references. And they're not tied in reality. It's a mathematical transformation from the original cross power matrix to this set of virtual references. On the right side shows the method we're using. We're using singular value decomposition to do this. And then when we rank the singular values, we have values on the diagonal value, and we have zeros on the off diagonal value. And when we look at the reference auto power matrix in the lower left corner, that's the scaling factors on those singular values. Okay, so we're going to go through this decomposition step inside the software using principal component analysis. And then within that principal component, there's a fixed phase relationship between the responses, like I said, but there's not a fixed phase relationship with the other principal components. So in the lower right, we're showing you phenomenon 1, that's principal component 1. Middle is phenomenon 2, that's principal component 2. And then phenomena 3 would be principal component 3. So within phenomena 1, there's a phase relationship between all points. Within phenomena 2, there's a phase relationship. Within phenomena 3, there's a phase relationship. But there is no phase relationship between phenomena 1, phenomena 2, or phenomena 3. So there's not a phase relationship between the principal components. So it's very important when we add up the contributions of those different principal components, we have to do it in an RMS manner. So we're going to square those principal component effects before we sum them together, because there's no phase relationship between those principal components. So the last point there, we recombine those principal components to get the total contribution by summing in an RMS manner. So we're going to measure cross power that are going to be partially coherent. We're going to use that in principal component analysis, to come up with a set of virtual spectra that have a set of virtual references that are completely uncorrelated. And then we'll get a new set of reference autopowers and virtual spectrum. So we're going to go through the singular value step, and then we're going to get some virtual references and to diagonalize the matrix. And now we're going to have the virtual autopower matrix with the off-diagonal term set to 0. So those are the different steps. The values of the reference autopower matrix basically are the singular values scaled. So the input is your cross-powered matrix, and the output is going to be a set of virtual spectrum and a set of virtual autopowers that we can study and use inside the transfer path analysis. Okay, so here it is again, objective, find a transformation enabling this. So we start with a cross power with a set of physical references, and we end up with a set of virtual spectra using a set of virtual references. And we're going to use those virtual reference spectrum inside the transfer path analysis. Okay, so the output of the principal component analysis are the principal component autopower matrix. So these are the autopower of the virtual references. We have a new orthogonal virtual reference set. So those have items on the diagonal, but no values on the off diagonal. U is a unity eigenvector matrix, so that's part of the math there. And then the principal component autopowers are the weight of the independent phenomena. Those are your principal components. We end up with a virtual cross-power matrix. These are single reference cross-powers of the original references or responses with respect to the new mutually uncorrelated virtual references. And these virtual spectra are what we're going to use in matrix inversion to calculate the forces. Okay, so these are the reference virtual spectra. You get one set of uncorrelated weighted spectra per principal component. Input's going to be into transfer path analysis. Each principal component is considered as one operational case. And then we're going to sum up those operational cases in an RMS manner. There's a consistent phase relationship within each principal component, but not between principal components. That's why we sum them up in an RMS manner. The other outputs of the principal component analysis, we can look at the virtual coherences. This is the coherence of the original references and responses with the new virtual references. So that tells you the percent of energy in each response related to the new principal components. Virtual coherent autopower is a part of the autopower of the original references and responses, which is coherent with the virtual reference. And we can also look at the sum to virtual coherence and coherent autopower. This indicates how well a subset of virtual references describes the structure's dynamic behavior. So these are checks to see if the virtual references being used are appropriate. They're also a good check to see how many principal components you want to use in the transfer path analysis study. So this is a required data. So here is a matrix of all possible references and responses. So we need to have the cross power matrix. So we need the reference autopowers. So we don't need the lower diagonal, you don't need the full one. So basically you need the autopower matrices, you need the reference autopower matrix between all of your references. And then we need all of the cross powers from all of the responses with respect to all of the references. Okay, and then if you have the autopower of responses, that can be used for data checking. So this would be your targets. You can have the autopower of the targets to compare with the total contribution of the targets at the end of the TPA. So left side is required data, reference autopower matrix, cross power matrix to all the references. Right side is your targets. That's nice for data checking. So multi-reference TPA, the overview. So basically, we're going to take the original cross power operational data for all of the references. We're going to use principal component to decompose it into a set of virtual reference at these virtual references we find. Then we're going to do single reference TPA analysis, usually using matrix inversion, using this operational data. And then we superimpose the results for each of those independent phenomena. So basically, we're going to look at principal component 1, calculate the force via matrix inversion with the virtual spectra, do that for principal component 2, principal component 3, etc. And then we're going to look at the total contribution by doing an RMS sum of the contribution due to each of the principal components. Okay, so here's an example of 2 different approaches for principal component analysis and multi-reference TPA. There's 2 purposes. One, do you care about capturing all the energy that enters the car? Or do you care about approach 2, capture all the energy that's relevant inside the car? And I have companies doing both approaches. So the first approach, you want to capture all the energy that enters the car. So then you want to put the references at the wheel center vibrations. So you're going to have XYZ references at each of the wheels. So that's going to have 12 references. The principal components are the structural phenomena feeding into the car as it's driving over the road surface. This can be used for ride comfort analysis, for example. Usually we have 6 to 8 structural phenomena acting on the structure, so getting into the vehicle. Not all of them generate noise, so not all of them are important. So basically, if I have 12 references, I'm going to have 12 virtual references, and it's going to calculate 12 principal components operating on the car. And you're going to rank those 12 principal components and look at them and see which ones are dominant. And if you only have 6 principal components that are dominant, you only include those in the TPA. If you have 8 that are dominant, you would include 8 in the TPA. So you're going to want to rank those principal components of the 12 that are calculated and see which ones you want to use. The other ones are noise or may contribute to poor results. Second approach is I don't really care what's coming into the car as far as forces, but I want to look at the energy that's getting to the driver, and I only want to study what components are actually getting to the driver interface. So then the references would not be the wheel centers, the references would be the interior microphones. And here we're using 4 because we're expecting to have 1 to 2 acoustic phenomena at each frequency that are dominant. So you need to have more than 2 references. So then the principal components, rather than structural phenomena, they're acoustic phenomena acting inside the cabin. Limited number of acoustic phenomena, 1 or 2. So again, we would rank the principal components. We'd look at them. And if we only had 1 or 2 that were dominant, we would only consider 1 or 2 principal components in the TPA. We would not consider all 4. So we rank those in importance of interior acoustic energy rather than structural energy. And then one of the issues with the second approach is the estimated force not representative of the real structure. So if you care about getting accurate forces at the wheel centers, approach 2 isn't the way to go. Approach 1 is the way to go. Okay, so 2 different ways to approach it. One uses 12 references to calculate the cross powers, and those references are at the wheel centers. The other one uses 4 references to calculate the cross powers, and those are at the interior microphones. Okay, so this is the same slide. Basically, you measure the operating data. We want responses at all of the targets and all of the indicators. The indicators are the accelerometers used to calculate the force. We also have either 4 references if we're looking at acoustic references, or we have 12 references if you're looking at wheel centers as references. We process that to get the reference auto power matrix and the cross power matrix with respect to the references. We go into principal component to calculate these virtual references. We use that to calculate the virtual cross power or the virtual reference cross powers. And then we use that inside a single reference TPA, normally with matrix inversion. And then we sum up the contributions of the different principal components in an RMS manner. Okay, so these are the steps. I measure the throughput in spectral or signature, use multi-reference TPA add-in to calculate multi-reference cross powers in the throughput processing workbook, use the principal component analysis add-in to calculate the principal components in the virtual spectra, then we feed that into transfer path analysis. You measure the FRFs. Traditional way to measure the FRFs, use impact testing, use spectral testing, use NEMO FRF, and we feed those FRFs into TPA. So a couple add-ins we need. We need the multi-reference post-processing add-in to calculate multi-reference cross powers, and we need the throughput processing add-in to calculate those cross powers. Once we have those multi-reference cross powers, we need the principal component analysis add-in to calculate the principal components and the virtual spectra. Okay, so a little bit more complicated than traditional TPA. Got some math to do or massaging of the data to do before we can begin the TPA study. So now I'm going to show the steps, and then after I go through the steps, we'll go through the software and I'll show you how it's done. So here is the cross power calculation. In this example, I'm going to use Brain. So in the training class, we use two almost academic examples to explain concepts, just to make it a little bit easier. We use a beam example, and the beam example has a couple responses on a beam and two shakers on the beam that we have the same signal going to two shakers. So if you were to do that without principal component analysis, you over-predict the results. And then when we do principal component analysis on this beam data, we realize we don't have two sources. We really only have one because we fed the same signal to two shakers. And that's example one we use in the training class. This is the second example I like to use. And here I have a toy plane, and I have a shaker on each wing. On the right wing, I have a shaker. At the left wing, I have a shaker. So that's simulating the engines running. And then I have three references. I have a reference at the tip of the left wing, a reference at the tip of the right wing, and a reference at the tail. And I'm going to calculate cross powers with those three references. And I'm going to do stationary with 100 averages. So when it runs out of data, it just stops. So maybe it's only going to get 70 or 80 averages. I just put a big number, and I'm going to do a linear average. And then I go into principal component analysis, and I bring in that cross power matrix. So if I were to display the top three rows, that is your reference auto power matrix. And if we had completely uncorrelated references, I would only expect values on the diagonal. And you'll see that I have values on the off diagonal. So that's telling me that my references are partially correlated. And then below row 3 is the cross power matrix that I can display and look at. So basically step 1 is to define the data source, and that data source has to have cross powers. And the status verification okay means if I have data across multiple runs, it's a requirement to have the reference auto powers in every single run. So maybe I'm testing 200 points on this plane, and I'm not rich, so I don't have enough channels. Maybe I only have 20 channels on my front end. And if I'm going to have references at left wing 1, right wing 1, and tail 1, those three reference auto power matrix have to be in every single run. So every run needs those three measurements in it. And then I could rove the 17 other channels across the entire plane. But it is a requirement that if I have multiple runs, these reference auto powers have to be in every single run. And this worksheet checks for that. One of the other things we suggest is if you've got data across multiple runs, it's important to check for repeatability. So I would display my reference auto powers across all my runs and make sure my runs are consistent. If you're on a dyno, that's probably fairly simple to do. But if you're driving at a test track, you want to make sure you're on the same portion of the road and the same part of the lane to try to help with that repeatability. So this worksheet does check for that. And if you don't have the reference auto powers in every run, the status will be red. And you'll probably call me and I have to help you sort through your data. But that is a requirement. Then once we find the data selection, once we have all the cross powers and the reference auto power set up, then we go to calculate. And I would suggest turning on principal component auto power to check to see how many principal components you have and how many are dominant. And then I would also turn on referenced virtual spectra. Referenced virtual spectra is the data that's going to be used in matrix inversion for TPA. So that is a requirement you minimally need the referenced virtual spectra turned on. Principal component auto power we'll talk about. I'll also talk about when I show the demo virtual coherence, coherent auto power, as well as virtual cross power. Then we go into transfer path analysis, and then it's set up exactly as any standard TPA. So I have 3 targets. I have my left wing, my tail, and my right wing at point number 1. I have 2 paths. So I have engines at point 4 at left wing and right wing. And then I have indicator data along the left wing and the right wing that's going to help me calculate the forces in matrix inversion. And then the trick with multi-reference TPA is to turn on multi-reference TPA on the right side underneath operational data cases. And then once I turn on multi-reference TPA, it's going to look for principal components in the input basket. So you can see my selected data cases are PRCM number 1, PRCM number 2, PRCM number 3. Those are my virtual spectra from my 3 separate principal components. It's also turned on RMS sum, and it won't let you turn it off. So we always want to look at the contributions across your operational data cases in an RMS manner. So it's going to turn that on automatically for you, and it won't let you turn that off. So unique thing for multi-reference TPA, at the top of operational data cases, you have to turn on multi-reference TPA. It's only going to look for principal components in the input basket. And it forces you to turn on include RMS sum of cases, and it won't let you turn it off. And then once we get forces, the rest of TPA is pretty much the same, except you don't want to look at the contributions due to data case 1, 2, or 3, which is your principal components. You only want to look at the different RMS sums. And then it's a software demo. So I'm going to do a demo now and switch to TPA. And put my TPA here. And I don't currently have anything in the input basket. So let me put some data in the input basket. So I just restarted my test lab. So I'm going to add throughput data into the input basket because I need to calculate cross powers. Okay, so this is my throughput data. So I've got operational data at my targets, left wing, the tail, and the right wing 1. That's going to be used as my references in my cross powers. And I also have all my operational data as well as my target data. And then I need to add the FRFs as well. So let me add the FRFs to the input basket. So these are my FRFs. So in my input basket, I have my FRFs and I have my throughput data I'm going to use to calculate the cross powers. Okay. So then I go to time data selection, replace some input basket. So there's my time data. So I have 100 seconds. Go to time data processing, select all my curves, go to stationary. So I'm going to do 100 averages, and I can either do energetic average or I think the slide said linear average. Okay, but you can do either way. I guess I'll do linear average here. Go to FS acquisition. I have it set up to be about 0.2 hertz resolution, so I'm going to do a 1024 block size. And then I go to channel processing. I don't have any acoustic data, so I go to the vibration group. I'm going to calculate cross powers. Cross power is power. And then I'm going to turn on my left wing, my tail, and my right wing here. Okay, so I have the 3 references turned on. Okay, and if you wanted to see the add-ins, under Tools Add-ins, in order to turn on that, I need signature throughput processing. Okay, that gets me the time data processing worksheet. And in order to calculate multi-reference cross powers, I need this multi-reference processing, which is an additional 35 tokens. Okay. And I think that's all I needed. I needed to calculate stationary averaged, and I also need to calculate multi-reference cross powers. And then I can call it TPT, let's call it TP class, so I know what it is. Okay. So there I have them. And then I go into the principal component analysis worksheet with those cross powers. So that requires 25 tokens. And that gives us this multi-reference processing worksheet. So this is the first add-in. It gives you this. So I've got one run here. and it's the most recent run. So this is this TPA class run I just calculated. If I switch from runs here, I can look at matrix per run or matrix all runs. Here I only have one run, so these two views are going to be the same. So I'm going to go to matrix per run. And this is my reference auto power matrix. So these are my 3 reference auto powers. If I put this in log or dB, those are my 3 reference auto powers. So if my references were uncorrelated, all the off-diagonal terms would be close to 0. And you can see here that is not the case. So as I turn on these reference auto powers, and if I look at the full 9x9 matrix, I can see that I have values on the off-diagonal. So these references are partially correlated instead of uncorrelated. If I want, I can look at the cross powers. So these are the cross powers with respect to the first reference, cross powers with respect to the second reference, cross powers with respect to the third, okay? And then this is an auto power of my response. Okay, so you want to make sure this is okay, and you want to make sure verification is okay. If I had multiple runs, I could go and use the pull down to step through each of the runs and see if it was okay. And if I had multiple runs, I could go to matrix all runs and make sure that this is okay, and I could display the data across all the runs. But here I only have the one run. And if I go to runs, that would be the runs. So there's not much to this worksheet, these 3 steps. Okay, main thing is it has to have a green status, and it has to say verification is okay. Then I go to calculate, and the only thing we need to do for multi-reference TPA is to calculate the reference virtual spectra. That's the only input you need for transfer path analysis. To do some steps, I'm always going to turn on principal component analysis, and those may be the only 2 things you want. I'm also going to turn on these other ones just so you can see what they are. And now I'm on the PCA tab, and I'm going to calculate principal component analysis. So I'm going to calculate all of these. If you had mixed unit, you can do some balancing. I don't have mixed units, so I can actually say no balancing. But if my operational data was a mix of strain and acceleration, perhaps I want to normalize that operational data by the RMS levels, then I could do automatic balancing per unit. Or I could also do automatic balancing per reference. Here I'm just going to do no balancing. It'll rank, I only have 1 unit, so that doesn't matter. But it's going to rank the effects of each of the references equally. And then I'm going to just calculate. And then down at the bottom, it gets kind of confusing because if I show 1 block, you can see in the legend it is actually showing several because I have the sum turned on in the total sum, and I'm going to turn off measured. So that way, if I highlight 1 thing in the table, it's only going to show 1 thing. So if I were to highlight all 3 of these are my 3 reference auto powers. And if they were all dominant on a dB or log scale, I would expect them to all have about the same level. And if I go here to a log scale and put a cursor on it and put a cursor legend, so you can see there that 1 is 1e to the minus 3, 1 is 185e to the minus 6, and 1 is e to the minus 9. Okay, so they are several decades apart. That tells me I might have only 1 dominant principal component. In some areas, I may have 2 dominant principal components, but for sure, it doesn't look like I have 3 dominant principal components. And sometimes, if I look at the defaults here, which one is it? I think it's under general. A lot of times when you go into the software, the lower curve is hiding. So you can turn some of this stuff off, or you can manually set the limits so you can see that last curve, because a lot of times that last curve is hiding. So for example, if I set this to fixed, maybe I put this bottom at minus 50. Okay, you can see I don't see that last curve. And a lot of the times when you come into this worksheet, you see that. And if you look closely at the legend, it may tell you all values are out of the limit range. So that's kind of a clue that you have to make this lower. And that may change a little bit between releases. Maybe this release does a better job of it because I'm using 2019. But some of the older releases, I know I had to kind of look for that last curve. So this is a reference auto power matrix. So this is telling me when I do my multi-reference TPA, I may only want to consider one or two references. I probably don't want to consider all three of these principal components because that blue curve is quite a bit lower, except perhaps maybe at this one frequency here, but it's still quite a bit down. It's 40 dB down from the first curve. But that's a good way to use this. Another way to look at that is this is the auto powers with respect to the first virtual reference. They're fairly clean. This is respect to the second virtual reference, fairly clean, comparatively so. So these ones are really poor. So if I look at the virtual auto powers with respect to the third principal component, it's quite a bit noisier than the first two. So that also tells me I want to perhaps discard that third principal component. The other things we can look at is if I look at the coherence. So this is the coherence with respect to the first principal component. This is the coherence with respect to the second principal component. And this is the coherence with respect to the third. And you can see it's fairly low. So this is another check to see if I want to consider that third principal component. And I would say no based on these virtual coherences. You can also look at partial coherences. I don't have that calculated. Oh, these are the virtual spectra. So these are going to be the input to matrix inversion. So if I highlight the virtual spectra with respect to the first principal component, they look pretty good. Not so much with the second one, but still okay, but really noisy with the third one. So again, this is another sign that I don't want to consider this third principal component. And then if I go back to my navigator, so now what I need to do is go to my current project, and I'm in the multi-reference TPA section. And this is the last one I just calculated. So I'm going to add these reference virtual spectra to my input basket. So now in my input basket, I have my FRFs and the virtual spectra and the throughput data that I no longer need. So now I can go to transfer path analysis, and I can set up my TPA model. So if I read my input basket, so my targets are these three here. Okay, so these are my three targets. Node 1 at the left wing, the right wing, and the tail. These are my paths. These are the four. This is 0.4 at each of the wings where the engine is mounted, and that's where we have a shaker operating. And then my indicators here are the indicator points that will be used to calculate the forces at 0.4. So the indicators are always extra points used just to calculate the force. And then once you have the force, we're going to multiply that force by the FRF at the paths to calculate the contribution from that path to your target. And then if I get rid of my operational data here, and now if I say I've got multi-reference TPA, I'm going to turn that on. Hit read input basket. It finds the third principal components. And based on looking at my reference auto power matrix and my virtual coherence and my virtual spectra, I don't want to use this third principal component. So I'm just going to use two. And then I go to FRF selection, make sure my FRFs are here. So these FRFs are going to be used in matrix inversion to calculate the forces. Once I have the forces, these are going to be used to calculate the contributions to the targets. So that's unrelated to multi-reference TPA, just stating that again. Find my operational data. So here's my operational targets. And then these are the operational spectra for each of the principal component 1, principal component 2. So now I go to TPA loads, go to matrix inversion, clear all my forces here. And now I'm going to create full matrix. It'll take a little bit, so it's fast. So this is a 10 by 2 matrix. So I have 2 paths and I have 10 indicators. So that's why I have a 10 by 2 matrix. If I look at the condition number, which is basically a quality indicator on the matrix before it's inverted, it is fairly well conditioned. And that's because I have a very good overdetermination of 10 indicators to calculate 2 forces. And then normally we want this condition number to stay below 100. So it's below 10, so I'm very happy with that condition number. And then I can look at the forces. So I can look at the forces calculated with the first principal component, and I can look at the forces calculated with the second principal component. Once I have those forces, I can go right to TPA. I can pick the target, pick a group. I'm going to look at RMS sum and update the display. So now I can look at the total contribution due to left wing 4 and right wing 4. You can also look at the vector contribution, so standard TPA stuff. So I can look at this vector contribution. And again, I want to look at the RMS sum. Look at it in complex here. Okay, so since I'm summing in an RMS manner, you can see there's no phase, but I can look at the measured versus the total contribution. You could also look at each of the different contributions if you want. Okay, so that's the principal component 1, principal component 2, but usually we're most interested in this RMS sum. If I look at the path specific results, and if I look at my first target, down in the lower right is the measured data in green and the total contribution in red, and the contribution to left wing 4 is the blue curve, and I can look at the contribution to right wing. So I can see here that the total contribution and the measured data is very close. If I look at the right wing target, I get similar results. And then if I look at the tail, I can see what part of the contribution at the tail is coming from the left wing and what contribution is coming from the right wing. And again, I have a very good correlation between the measured data, which is green, and the total contribution, which is red. Okay, so that's multi-reference TPA. If you wanted to play around, I could go back to my TPA model, go back to my definition, say I want to look at this one. So now I'm going to consider the third principal component. I have to go to operational data, find it, because you can see it's missing now, add from input basket. Now I want to go to TPA loads. So the loads are -43, -51.9. So I can clear all the loads, calculate the full matrix. So they didn't really change, okay? So in this particular data set, we don't see a lot of change by adding that third principal component. That's not true all the time. So I've seen much different results by adding principal components that you should not. This is a little bit of an academic example since it's a more controlled environment, since it was a toy plane. And again, if I wanted to look at the contributions, I could do that. Other thing I wanted to show is under multi-reference TPA in Calculate. Here we can calculate FRS directly from the cross powers along with multiple coherence. I can also calculate partial coherence due to any one of the references. So that's kind of neat. So that's something we can't do in time data processing. So there's some nice tools here in multi-reference for calculating FRS in multiple coherence, as well as calculating partial coherence that we don't have under time data processing. So that's kind of interesting. The other thing that's nice is FRS with singular value decomposition. Here we can calculate how many principal components we have in that cross power data, and then decide to use that when calculating the FRS, and we'll calculate those FRS with singular value decomposition. And if our condition number is bad, we can remove some of the singular values with this treatment here. And I can remove a fixed number, a relative number, and an absolute number of our singular values. So this is very similar to matrix inversion. I get that question not a lot, but quite a bit over the years. I've been with Siemens/LMS 20 years now. And people are always surprised if I use this multi-reference processing add-in, and rather than cross powers, if I calculate FRS, why is it different every time I turn on additional references? And that surprises people. So in a modal context, as long as your shakers are uncorrelated, I can turn on 4 references and calculate the FRF. And that FRF with respect to reference 1 or reference 2 or reference 3 or reference 4 never changes. It's a system characteristic of your structure. And that is because your references are perfectly uncorrelated. In this case, our references are partially correlated. So if I were to calculate an FRF with one reference turned on and look at the FRF from the tail to left wing 1, it would be a certain FRF. And if I turned on another reference, that same FRF from tail to left wing 1 will be different. If I turn on another reference, it will be different again. And that's surprising to people. And I've had a couple of people think it was a bug, and it's not a bug. Let's see here, left wing, illustrate references. So be aware that if your references are partially correlated, and if you calculate transmissibility functions, which is FRFs under operational condition with operational responses, your FRF will change every time you turn on a different reference. And that's dangerous, especially if you're using something like operational path analysis. So a better way to calculate those FRFs when you have partially correlated references would be to calculate cross powers instead, okay? And then once you have those multi-reference cross powers, take it to multi-reference processes, calculate, and maybe you want to calculate FRFs with singular value decomposition. And that is probably more accurate. Not 100% correct either, but much more accurate than calculating FRF under time data processing, which assumes they're perfectly uncorrelated references. Other thing I was going to show is if I go back to my slides is this is kind of an academic example, but we do have other examples. So that was the software demo for the plane. And if you have questions on that, please let me know. We also, in the TPA Masterclass, which has been held in Europe a couple of times, this is a full vehicle we have. It's actually a Dodge that we've done a lot of testing over the years with. So we've got quite a few measurements on it. And then we did multiple acquisitions. So some of the things I mentioned, you should check repeatability. So one of the things we suggest you do is if you have data across multiple runs, you want to compare the runs. And when you look at your targets, which are 4 microphones in the car here, you want to make sure that you see consistent peaks, and those peaks have similar amplitudes. So here we've identified for the front microphones and the rear microphones on the left side and the right side, some peaks that were interesting to us we wanted to study. And then we went through principal component analysis, and we did it 2 times. We went through principal component analysis only using the first run. So basically, we had the same data across multiple runs, which was steady state, driving down at a constant speed down a part of the road. And we looked at multiple runs, and we decided that one of the runs looked better than the other ones. And that was run number 1. So we choose to do these studies just for the first run only. And exercise 1 used the 12 wheel center accelerometers as the references. We use that to calculate the principal components. One of the tricks we like to do is animate those principal components. So you can take those principal components into operating deflection shapes and then see if it looks like parts of the road you're driving over. So perhaps you've got a sinusoidal part of the road, and when you animate that frequency, it's got a certain shape. Okay, so you can animate each of those principal components, and they may provide insight into things the road is doing or things the front and the rear suspension are doing. So you may see modes of the suspension systems, for example. So animating the principal components is useful. Then we did a second study where we used the 4 references as the microphones. And again, we used the same first run, and then we did the principal component analysis. And again, we can animate those to look at the different acoustic phenomena acting on the structure instead of the structural phenomena. And it's a little bit hard to see in the plots, but in the lower left corner, the measured data is this purple curve. And then principal component 1 is the red curve, and it's rather low. But then when we looked at the first 3 principal components, it looks fairly good compared to the measured data. So there we discarded the 4th principal component, and we only kept 3 in. And then actually the slide there says number of principal components was equal to 2. So we probably could have looked at principal component 1 plus 2 and not all 3. And the lower left slide shows that for the rear left microphone as well as the front left microphone. On the right side, we're looking at the 12 references at the wheel centers. So there we have 12 structural phenomena. And it looked like when we looked at the principal component auto powers, we had 6 of them. So the slide is showing on the left side, for the rear left, we're showing you the measured data as the purple curve, and then the sum of all the principal components as the blue curve, and the green curve is the first 6 principal components. And then we do that for the rear left and the front left. And it looks like on the lower left, it looks like we did show you PC1 plus 2. That's the green curve. And then the red curve is all 3 principal components. So there is a difference between the green curve and the blue curve. And we see the same thing on the right side. If we look at the green curve, which is the 6 principal components, and the blue curve, which is all 12 principal components, they're similar, but a little bit different. And then we looked at the summed virtual coherence and the summed virtual coherent autopower. So after the class goes through the exercise, this is the results of those two different studies, one using the 12 references at the wheel centers and the other one using the 4 targets as the references. So this is a more realistic road noise analysis study. Exercise 3, vehicle status analysis. So here what we're trying to do is, if we're looking at the contributions at the left ear and the right ear, in the front and the rear, what portion is coming from the front suspension and what portion of the noise is coming from the rear suspension. So we can look at the principal components by summing up the 6 front row reference accels and also the principal components using the 6 rear. And it's interesting that at low frequency, the rear suspension tends to dominate. In the middle frequency, the front suspension dominated, and at the higher frequencies, the rear suspension dominated again. So there we can see the contributions to the total, front and rear together, is the grayish or black curve. Red is the rear contribution only, and green is the front contribution only. So it gives you some insight on the analysis. That is all I have